Okay. Hello, everyone. My name is Dexiang Hong. Today, I will introduce our Cascaded Temporal Attention Network in generic event boundary detection challenges at CVPR 2021. Our team has 5 members: Dexiang Hong, Congcong Li, Long Yingwen, Xinyao Wang, and Li Bozhang. Congcong Li and Dexiang Hong contribute equally in this work. My report today is divided into 3 parts: a motivation, approach, and experiment. The task of generic event boundary detection aims to localize the moments that breaks a longer event into shorter temporal segments. The task has following challenges. First, how to fully understand the contextual information of the video clips. Second, it is difficult to determine whether a frame is the event boundary or not. To handle the first problem, we use audio and visual inputs. Further, we design a temporal attention module, which consists of a temporal component and an attention component. To handle the second problem, we propose a cascaded classification module using different ground truth labels produced by different relative distance thresholds. This is the overview of our approach. At each candidate boundary position time t, we organize n frames before and after t to construct a video clip as our network input. The network aims at classifying whether the candidate time position is the event boundary or not. In detail, our approach consists of 5 components: dynamic sampling strategy, visual feature extraction backbone, temporal attention model, audio model, and a cascaded classification model. First, we will introduce our dynamic sampling strategy of input frames. Videos in Kinectis GBD are recorded in different FPS. We counted the FPS distribution in the Kinectis GBD training set. The results are shown in the right figure. We can see 71% of video FPS around 30, 21% of videos FPS in the range of 20 to 27, and around 10% of videos FPS below 20. So, fix the frame sampling strategy may include redundant information for large FPS videos, while lack necessary contextual information for smaller FPS videos. To solve the problem, we use dynamic sampling strategy. Intuitively, we sample 1 frame for every 8 frames. Second, I will introduce our feature extraction backbone. We use channel-separated convolution network pre-trained on IG and Kinectis dataset. Specifically, we modify the temporal stress of the CSN from 1222 to 1111 so that we can get the feature embeddings in the original temporal resolution. Thirdly, I will introduce our temporal attention model. Our temporal attention model consists of temporal component and attention component. The temporal component is responsible for extracting temporal context information, and the attention component is responsible for understanding the semantic of each input video frame. Specifically, for temporal component, we stack several dilated 1D convolution layers in temporal domain to increase the receptive field. Meanwhile, we use a bidirectional LSTM to capture temporal information, which can process sequences of video frames in the temporal space. For attention component, 4 self-attention layers are adopted to process the input features. Fourth, I will introduce our audio component. Joint audio visual learning is the core to human perception. For many video understanding tasks, audio could be very helpful. We extract the audio from the original videos and use short-time Fourier transformation to convert the audio representation into the frequency domain. Then, 4 1D convolution layers are adopted to extract the temporal features of the audio inputs. Then, we concatenate the audio feature with visual features and fit them into the linear classification layer. Fifth, we will introduce our cascaded classification layer. Since the event boundary is taxonomy-free, it is difficult to determine whether a frame is the event boundary or not. The official evaluation protocol addresses this problem by using relative distance, which indicates the error between the detected and ground truth. Then, given a fixed threshold mu for relative distance, we can determine whether a detection is correct or not. However, in our training phase, it is a problem that how to set a proper mu. When mu is high, the positive samples contain more ambiguous frames and make the classifier confused. When mu is low, the positive is more accurate, but it is difficult to assemble enough positive training examples. To solve the problem, inspired by Cascaded RCNN, we propose the Cascaded architecture to gradually refine the classification results. The Cascaded classifier are trained sequentially, using the output from the previous stage. Specifically, given a sequence of classification heads H1, H2, and H3, we train this classifier using different ground truth labels. These labels are produced by decreased ground truth relative distance threshold, mu1, mu2, and mu3. Then, the output classification score is used as a mask with threshold tau n to fill out easy negative samples. The next stage detection head further refines the positive samples using previous head's mask by utilizing more accurate ground truth labels. To fully understand the contribution of each component, several ablation experiments are conducted. We report the results on our local validation set. We can observe that with this method, we improve the F1 score from 0.615 to 0.814. Finally, we assemble 9 models with different parameters. Our final result on the Kinect GBD test set achieved 0.833 F1 score. That's all. Thank you.